This video is to coincide with the iodine clock reaction from general chemistry, specifically just to go over the datasheet that we'll be using. And while there are multiple iterations of the iodine clock reaction, the specific one we're going to be using is formally called the Kinetics of the Oxidation of Iodide Ion by Hydrogen Peroxide. Now, key here is as you get into the lab, just make up all of your solutions 1 through 11, but as you're preparing them according to the chart in your procedure data sheet, make sure you do not add the hydrogen peroxide until you are ready to record your timed trials. And for the trials where you're going to be cooling the solutions in an ice water bath, you'll cool the solution with everything besides hydrogen peroxide in it, and then you will also, in a separate beaker, cool a little portion of hydrogen peroxide for just that solution. And so to reiterate, prepare these solutions as shown except with hydrogen peroxide, and then only add that last component when you are ready to record the trial, the time trial for that specific solution. Let's see. Now, for your data sheet, this is the only questions that you have to submit for your post-lab assignment. Question 1 on your data sheet is calculate the initial molarity of thiosulfate ion in each reactant mixture. Note it is the same concentration for all 9 reactions. This is easy. Start with the initial concentration and initial volume. Knowing the final volume, calculate the final concentration. So, according to our chart, once your sodium thiosulfate buffer solution is made, it will have a concentration of 0.001 molar. And if you take 25 milliliters of that solution, or 0.025 liters, what we have is 2.5 times 10 to the negative fifth moles of sodium thiosulfate. And since in each of your trials, the final volume is going to be 100 milliliters, we can take that mole amount of sodium thiosulfate, divide it by 0.1 liters, and that gets us to the molarity, or the answer for question 1, 0.00025 molars of sodium thiosulfate. Question 2. If the entire amount of thiosulfate ion reacts according to equation 4, what is the molarity of iodine formed by reaction 1? Well, going to our procedure, we see that we had 2 chemical reactions. Equation 4 is where we are using up our thiocyanate anion S2O3 to form iodide ion, and then question 1, or in equation 1, that's where that formed iodine ion is reacting to form molecular iodine, iodine, or I2. So the first part to solve this is simply what is our concentration of thiocyanate anion? Well, since we have the concentration of sodium thiocyanate, once that breaks up into ions, it will break up into 2 ions of sodium and 1 ion of thiocyanate. The latter is the one that we're concerned with because it's a 1-to-1 ratio. Our starting concentration of thiocyanate anion is 0.00025 molars. According to reaction 4, if we use up all of that thiocyanate ion, that is going to form 2 moles of iodide ion for every 2 moles of thiocyanate anion that gets used up. And if we continue on into using information from chemical reaction 1, what we see is that for every 1 mole of molecular iodine that is formed, we need 2 moles of molecular iodine. So using the mathematical calculation set up in the middle, what we should get is a molarity of I2 being 0.000125 molars of molecular iodine. And then you would fill in that math for that box. Now, next part is going to be filling in this table, which has for each of your solutions a reaction rate in units of moles per liter seconds, or molarity per second. And then we have our concentration of peroxide, hydrogen peroxide, and iodine ion. Because this is instantaneous reaction rates, we're concerned with the initial concentration of both. So what you'll be filling in is the initial concentrations of H2O2 and I-. And then eventually we'll calculate the rate constant K or K prime as shown in our procedure. Calculating the reaction rate, since what we care about is the change in concentration of I2 per time, that will be, for any particular trial, the rate is just that concentration of I2, which we calculated in box 2, divided by the amount of time it took for that trial to happen, and that time would be in seconds. So the rate value that we plug in for solution 1 is simply 0.000125 molars of I2, divided by the amount of time you record for trial 1, however many seconds that takes. For rate 2, for solution 2, take the same concentration of I2, 0.000125 molars, and divide it by the time it takes for trial 2 to occur. So essentially, our numerator for our rate is the same for every solution. It's just that for our time trial, it will vary by the amount of seconds it takes for that trial to occur. So the only thing changing is the denominator of our trial. So that would be the only thing that changes, the denominator value, however many time and seconds you record, and then you'll just fill in your chart with the calculations you get from there. And again, that units will be molarity per second or molars per liter seconds. Next part, for the initial concentrations of hydrogen peroxide and iodine, well, what we need is to take into account our concentrations, or our initial concentrations of both of those, which we can get those values just from our chart, where essentially the total volume for each experiment is going to be 100 milliliters. All we need to do to find the concentration of H2O2 is taking its concentration, 0.06 molars, multiply it by the amount in liters that we are using for that trial, 10, 20, 30, whatever, and then divide it by the new total volume, which is meant to be 100 milliliters for every single trial. So, for example, let's say we want the hydrogen peroxide concentration in trial 1. Well, its stock solution, or its current initial concentration, is 0.06 molars. What we use in that trial is 10 milliliters of hydrogen peroxide, and the total volume of our solution will be 100 milliliters. Since these are both in the same unit, milliliters, we don't actually need to convert them to liters, because those units will cancel out. So 0.06 times 10 over 100 gives us the initial hydrogen peroxide concentration of 0.0060 molars. For trial 2, we would be using 20 milliliters instead of 10, so that ends up becoming 0.012 molars. For every trial where we end up using 30 milliliters of hydrogen peroxide, what we have is an initial concentration of hydrogen peroxide being 0.018 molars, and when the amount is 40 milliliters, that ends up being 0.024 molars. And for most of our trials, we're using 30 milliliters, so you'll see that the initial concentration ends up being the same for much of our experiment. Now, similarly, we can calculate the initial concentration of I-. Our chart we're working with potassium iodine, which as it breaks up, it is in a 1-to-1 ratio of breaking up into potassium ions and iodine ions. So our concentration, 0.06 molar of Ki, can really be taken as 0.06 molar of I minus, or our initial iodine concentration. Just like what we did for hydrogen peroxide, we can calculate the initial concentration of iodine anion by taking its initial concentration multiplied by the volume at that concentration we're using, divided by the total volume of our mixture. So the starting iodine concentration in solution 1 would be 0.06 molar, or whatever your stock solution says, multiplied by 30 milliliters over 100 milliliters, which gets us a iodine anion initial concentration of 0.018 molars. And as we continue on, essentially it follows the same math as what we did for H2O2. If you are using 20 milliliters of I minus, aka 20 milliliters of potassium iodine at 0.06 molar concentration, and sending that 20 milliliters to a final volume of 100 milliliters, the solution concentration for I minus would be 0.012 molars. And for solution 6 and 7, we have 10 and 40 milliliters, which gets us a concentration initially at 0.006 and 0.024 molars. And then for solutions 8 through 11, we're again using 30 milliliters of a 0.06 molar concentrated solution, and then bring it to 100 milliliters, which gets us to 0.018 molars for each trial. Again, this is based off of whether your stock solutions or the volumes you're adding are at 0.06 molar for hydrogen peroxide and or I minus. If you're working in a lab where the concentrations are different, then you would plug in those values as the initial concentration. So at this point, we have 2 or 3/4 of our chart already filled in, where column 1, the reaction rate, is just simply that change in concentration of I2, calculated during question 2, divided by what was the time in seconds that elapsed for that trial, and then that denominator being the only thing that changes and used to calculate the rate. And we just went over the ways to calculate the initial concentration of H2O2 and I minus, or hydrogen peroxide and iodine anion. Now at this point, we can't yet calculate the rate constant, as we've done with instantaneous reaction rates. Going into our procedure, we have a connection between K prime, our rate, and our hydrogen peroxide and iodine anion concentrations, which is the rate law using them. And as with any rate law for instantaneous reaction rates, each reactant is going to have some rate order. So our general equation right now is the rate of a particular trial equals that rate constant K prime multiplied by the concentration of hydrogen peroxide raised to X times iodine anion concentration raised to Y. So solve for the rate orders for both hydrogen peroxide and iodide using instantaneous reaction rate techniques. You're only going to do this, only choose data from trials 1 through 7 to determine rate orders for X and Y. In other words, choosing trials where we're not using a catalyst to arbitrarily speed things along, but just relying on the collisions of these two reactants by themselves. For example, trial data from trial 1 through 4 can definitely be compared with one another in order to get an average rate order for hydrogen peroxide, because for those trials, the concentration of iodide is staying the same, whereas for data in trial 3 and 5 through 7, you can take 2 trials from there and divide one by the other and do that a few times to get an average rate order for the iodide ion, because for those trials, the concentration of hydrogen peroxide is staying the same. And when you get your rate order averages for X and Y, basically if you see one consistent number, go with that. For example, if with a few of your trials you see 111 and one of your trials says 9.8, just take the value as 1. Perhaps that one trial with a weird rate order had a lot of error in it. But if all of your rate orders are around some similar value, take the average and then just round that to some whole number. For example, if hydrogen peroxide, all of your trials came out to be about 0.99, 0.98, 1.1, then just take the rate order as 1 for hydrogen peroxide. If the rate order you got for comparing multiple trials for iodine ends up being 1, 1, 1, and 13, just take the value as 1. And then once you have your rate orders for your individual chemical species, you can then solve for K prime, the rate constant, used for each trial, for each solution, because that rate constant will stay the same, or it should roughly stay the same for each and every trial, regardless of a catalyst or not. But you can solve K prime just like we did for instantaneous reaction rates, which is just going to be the rate of that specific trial divided by the product of your chemical species of interest, in this case peroxide, hydrogen peroxide, and iodine concentration, both raised to their respective rate orders. And remember that for your rate constant, when it comes to instantaneous reaction rates, that K constant will have specific units. It may be molars per second, 1 over molars seconds, or perhaps 1 over molars squared seconds. It depends on what you get for your rate orders for hydrogen peroxide and iodide. In any case, however it ends up being, remember to record your units as well as your rate constant magnitude. The last part will be with activation energy. Essentially, we're using the Arrhenius equation, which is the natural log of our rate constant equals negative activation energy divided by our gas constant multiplied by 1 over the temperature plus the natural log of our frequency factor. Identifying all of these symbols, K prime is just our rate constant from our rate law, which just was calculated for each solution. EA, that is the activation energy, which is in units of joules per mole. A, the frequency factor, is unitless. R, the ideal gas constant, is 8.314 joules per mole Kelvin. And then T is going to be in Kelvin, temperature of Kelvin specifically. If we look at this equation, we see that it resembles the linear trend line y equals mx plus b. So what you're going to do is, for specific trials, you're going to take 2 trials that are at different temperatures, 1 room temperature and 1 low temperature. In Excel, calculate the natural log of the rate constant for each trial and use that as your y values, and then calculate the reciprocal of the temperature in Kelvin, so 1 over T. Convert your temperature, whether from Fahrenheit or Celsius, convert it to temperature, convert it to Kelvin, then take 1 over that value, and you'll use that as your x values. And then plug them into Excel or any graphing program you have, and then from the resulting graph, find the linear trend line between those 2 points, and that will give you your y equals mx plus b, where b is just the natural log of your frequency factor, or more importantly, the slope m, which is equal to your activation energy over our ideal gas constant multiplied by -1. So for question 6, calculate the activation energies using equation 8 for the uncatalyzed and catalyzed room temperature reactions for solution 3 and 8. What is your conclusion? Now, the trick here is that you can't use two trials that have the same temperature. We have to use two different trials. So, what we're going to use is two trials for the uncatalyzed reaction. We'll need to use two trials where we do not add a catalyst and we're at two different temperatures. And then for the catalyzed activation energy, we'll need to use two trials at different temperatures where we do use the catalyst. So, in short, for the uncatalyzed activation energy, use data from two trials at different temperatures that did not have the catalyst, whereas for the catalyzed activation energy, use data from two trials of different temperatures that did have the catalyst. More specifically, we're told that we're looking for the activation energy from solution 3. Well, that's cool. Solution 1 through 7 were all at room temperature. The problem is solution 11, or 1 through 9, I believe, were at room temperature. Most of our solutions were at room temperature. The room temperature solution we're told to use specifically is solution 3. And the only cold trial that you did in lab that does not have catalyst would actually be solution 11. So take the natural log of the rate constant you calculate for solution 3 and 11, convert their temperatures to Kelvin and take the reciprocal, and use that as your X value for both solution 3 and solution 11. And then just find the linear trend line between those 2 points. And that you can use to calculate activation energy. We'll go into exactly how in a little bit, but for the catalyzed reaction, the two trials you should use, since we're concerned with solution 8, use data from solution 8 and 10 specifically, just because 8 is at room temperature. Solution 10, like with solution 8, has the catalyst and an equal amount of the catalyst. However, it is at lower temperature. So convert their respective rate constants into the natural log of that rate constant, or log base E, and then convert their respective temperatures to Kelvin and take the reciprocal. Plug those 2 points into a graphing software. Find the trend line between those 2 points, and then the slope equals negative EA over R. For question 7, essentially what we have here is calculate the activation energy for solution 9 and compare this to the value determined in solution 8. What do you conclude? Well, for solution 9, you're essentially using just a little bit more catalyst than in solution 8 or 10. Well, the only two trials that you can actually use is solution 9, of course, and solution 10. Solution 10 because that is at a different temperature and has catalyst, unlike solution 9. Whereas you can't use solution 8 and 9 together because they're at the same temperature. So just like before, use the rate constant for solution 9 and 10 and their temperatures, and as shown above, use those to get some trend line where the slope is equal to negative EA over R. In order to actually calculate the activation energy for the prior 3 graphs, comparing solutions set 3 and 11, 8 and 10, and 9 and 10, when you get your linear trend line, you're going to see y equals some number times x plus your y-intercept. Well, that slope m, that's the value we want, and that is equal to negative EA, or the activation energy, divided by R, the ideal gas constant. Simply solve EA each time. for those three prior graphs. And simply, if m equals negative EA over R, well then take the slope times negative R, which would end up giving us the activation energy. Therefore, the activation energy for each graph is going to be the slope times negative 8.314. And going back to our chart, even though R is in units of joules per mole Kelvin, that Kelvin would have gotten canceled out by multiplying by 1 over temperature. So what we end up getting is our units of activation energy being in units of joules per mole, specifically. So you calculated your three activation energies. They're in units of joules per mole. If you want to divide those, if they end up being very large numbers, you can divide them by 1,000 and then you would be in kilojoules per mole. In any case, the last question would be, what effect did temperature have on the reaction mixtures? I.e., what happened to your uncatalyzed reactions when you had them at a cooler temperature versus at a warmer temperature, like room temperature? And likewise, what happened during your catalyzed reactions, where one was at a cooler temperature and one was at a warmer temperature? And at that point, that concludes the entire data sheet, the guide to work through that. And for your post lab for the class you have with myself, this is the only stuff you have to submit for your post lab. So that concludes this topic for the iodine clock reaction. Likes and subscribes are never necessary, but appreciated, of course, and fun to see. And just around the 27-minute mark, glad to have you all, and peace.